as we go down, we'll talk about these most important circuit components. So the first one is what we call a source voltage. And a lot of times, it's really just a battery. But in electric circuits, it really doesn't matter exactly where the power comes from. I mean, you get into that when you actually build the circuit. But you know, from a theory point of view, it doesn't really matter as long as it has a certain voltage and it can push current out of it. We call it a source voltage. So the most common thing you're going to see in a classroom environment to draw or denote a source is a circle like this, right? Now inside that circle is going to be plus minus, and we've kind of talked about that a little bit, and you'll have a label somewhere over to the side, or maybe it's even inside. Maybe this is 20 volts, 20 V. And we've already talked about that. The units of a voltage, I mean, I'm just going to be kind of clear about this. The units, when you're talking about a source voltage, is volts. And I'm going to put in parentheses V. So this is volts, but just keep in mind that if you have a really teeny tiny source, you might be talking about millivolts, or microvolts, or nanovolts, or something really, really small. If you have a very large source, very high voltage, you might have kilovolts, or megavolts, or even gigavolts, or something like that. So you're using the metric system, but the base unit, I should say, this is the base unit. The base unit is the volt, all right? Now, most of the time in a class, you'll see your source written like this. It'll have a circle, plus, minus. We've already kind of discussed that. We've given you a little bit of the details of what this really means. Basically, your current, in terms of real life, the electrons in real life are coming out of this negative terminal and going back around through your circuit to the positive. But we already talked about the theory there. In reality, when we're drawing all of our currents, when we're doing all of our calculations, we're not going to consider the current coming out of this negative terminal, even though in real life that's really where the electrons are coming from. Instead, we're going to talk about what we call the whole current, which is the current. It's kind of fictitious, so to speak, but it comes out of the positive terminal like this. So it makes it much simpler. When you see plus minus on a battery or on a source or something, the current that you're going to use in your calculations comes out of this positive terminal and goes down around through the circuit, back up like that. So in most of the time, you're going to see the source written like that. But if you have a circuit that you're looking at, you might actually see it drawn like this. So I'm going to show you this. You might see it like this, with a bunch of little lines like this. Like this, right? And you'll also have some kind of volts, so maybe 9 volts. When you see it written like this, with a bunch of lines like this, it means it's a battery. It means it's literally one of those little batteries you can buy from the store. I mean, not always the case. Depending on who's drawing the circuit, they may have different intention. But most of the time, when you see it written like this, it means it's actually a battery. Whereas this can be anything. It could be a battery. It could be a power supply. Maybe I go buy a power supply from the store and I turn it up to 20 volts, right? Maybe it's got an adjustable knob and I crank it to 20 volts. So it's a generic symbol, this is. Usually when you see this, it implies that there's a physical battery in the circuit. Now let me show you a couple things very, very important. Usually you will not see a plus or minus written on this guy, but it's inside of the drawing. When you look at this, notice I drew one of these guys with a long line, and then I had short, long, short, long, short. And the last one I had is a short one, all right? So the short one, which is this one in this case, is always the negative terminal. The long one, which is always the case, you're always going to have a long and a short, it's always going to be the positive terminal. So even though it may not say it on your drawing, the long line that's at the top, in this case, is positive, and the short one's negative. Don't worry about how many little sandwiches I wrote there. That's not that important. It just depends on who's drawing it. But you can put as many as you want, really, right there. It doesn't really matter that much. It's trying to tell you that there's little cells kind of in series there adding up to this voltage. But from a big picture symbol point of view, all you're looking for is the long line telling you it's positive and the short line telling you it's negative. And the positive terminal here is where the current comes out and goes back around, just like in this case. So it's really the same thing. So you might see it drawn both ways, all right? But obviously you got to start somewhere. Power source is where we're starting here because every circuit's going to have a voltage source of some kind. Now let's look at this picture here of a real battery. If you inspect a battery long enough, you'll find that one of the terminals is labeled positive and one of them is labeled negative. So you can match that up to your drawing and kind of put it in place in the right orientation, but when you hook it up in the circuit, this is telling you this is the positive terminal, this is where the current comes out, negative terminal is on the other side. Okay, now the next most common circuit component, most important circuit component, is one that we've actually already talked a little bit about in the last section. It's called the resistor. And we talked about that in the context of the electric current, the current that's flowing. A resistor is trying to resist that current. It's really trying to slow it, not slow it down. It's not trying to slow the speed down. It's trying to limit how much current is in that circuit or maybe in that branch of a circuit. Maybe you have a circuit with two branches. Maybe you want a lot of current to flow over here. Maybe you don't want so much current flowing over here. It may depend on how you've designed your circuit. So we use resistors to pull that off. If we didn't have any resistors, we wouldn't really have a lot of control over how much current goes in different legs of the circuit. So that's really why they exist. So, number 2 is the resistor. And it resists current. Now the symbol that you'll see universally for a resistor, right, is going to be basically a zigzag, like this. And next to the zigzag you'll have some number. Maybe in this case it's written like this, 10 ohms. So the base unit of a resistor is equal to ohms, which you write as capital omega. Of course, you might be talking about kilo ohms or mega ohms or maybe even milliohms if it's a small version. So metric system applies, but the base unit is what we call an ohm. You'll always see a resistor drawn as a squiggly line. The squiggly line kind of represents, if you think about current coming through there, it's kind of like giving it a hard time. It's like trying to resist it. It's kind of like zigzagging, getting in its way. Think about it that way. That's why a resistor has that guy here. Now let's take a look at an image of a resistor here, and you'll see that it's just a discrete little component. You can put them anywhere in your circuit that you need, and different resistors that you purchase are going to have different values. Some of them may be 10 ohms, some of them may be 100 ohms, some of them may be 1,000 or 1,000,000 ohms, and you have different uses for different values. Now, the resistors are usually a little bit too small to actually print how many ohms are actually on there. So if you notice in this picture, there are different color bands that go around this resistor, and we'll talk about that a little bit more later, but the different color bands tell you, there's a decoder ring, so to speak, where you can look up the colors and figure out what the value of this resistor is just from the color bands that are on the resistor. So usually you will not see 10 ohms, 20 ohms, 30 ohms printed on the resistor, but these colored bands basically tell you what the value of the resistor is without actually having to print it on there. All right, now the next most common circuit component that you're definitely going to see in almost every circuit is what we call a capacitor. Now, I'm going to be honest with you, we're not going to talk about capacitors in really any detail until much, much later in the class, because we're going to spend a lot of times with resistors and circuits with resistors. But capacitors are very, very common. And in a nutshell, a capacitor is just a device that stores electric charge. You can think of it like that. You may have seen it in a movie as a flux capacitor, right? It's kind of like the movie language right there. A real capacitor is a device, it's a small device, similar size to a resistor, but it doesn't resist the current flow in the same way that a resistor does. What it does is it lets you pile up electric charge inside, and then at a later time, it lets you bleed that charge out, maybe to feed another part of a circuit. All right, so let me draw the symbol, and we'll come back around and I'll tell you a little bit of the practical reasons why you would use a capacitor. So what we have is what we call a capacitor. Right? Now, the symbol that you'll see most of the time for a capacitor will look like this. It'll have two parallel lines, like this. Now, the units, before I get and show you exactly why this is important, the base unit is the farad. Farad. So you might see that as F. But in reality, when you start purchasing capacitors or building capacitors or whatever, a farad as a unit of capacitance is an enormous amount of capacitance. It's an enormous amount of ability to store charge. So you're never going to find a capacitor at a store or in a mail order catalog with a value of 3 farads. It's never going to happen, because to get a capacitor that could store that much charge would be enormous, right? So almost always you'll actually see microfarads or even millifarads maybe, but most of the time you'll see it as microfarads. So this is at 1/1,000,000th of a farad. And so you might see a 2.4 microfarad capacitor or a 3.8 microfarad capacitor. And it's giving you a relative indication of how much energy can be stored in that capacitor. So let me go back full circle a little bit and explain what this thing is doing. The symbol is two parallel lines, but notice they are not touching, right? They are not touching at all in the middle here. So you can kind of think of the real capacitor as looking just like the drawing. You can think of a real capacitor as having a plate, right? A large surface area plate. You can't really see it because it's in the board, but imagine like a plate sticking out. And then another one right there. And the distance between them, I've drawn large here, but the distance between the plates in a real capacitor is incredibly tiny. In fact, the closer you can get it to the next plate over without touching it, the better. So if you wanted to build a capacitor, you could put air between them to separate the plates. But in real life, they might actually put plastic between them or some other non-conducting material. Something that does not conduct electricity goes between those plates. So you intentionally do not want those plates of the capacitor internal to that device to actually touch. You do not want them to touch. In fact, if they do touch, your capacitor won't work at all. So what's going on here is if I send a lot of electric current in here, this direction, then yeah, it's true, this is not connected. It will not continue on. However, electric charge will begin to pile up on this plate. It will begin to pile up on this plate. And because if you think back to your physics, anytime you have a bunch of electric charges piled up, what do you think is going to happen? If you charge up an object, right, you're going to get what we call an electric field, which don't be too worried about that or scared about that. What it basically means is if you charge a lot of, think about shuffling your feet along the carpet on a dry day. You've accumulated a lot of charge. Now you put your finger next to the doorknob and zap, the charge jumps off, right? That's because you've accumulated that charge. What you're trying to do here is allow this capacitor to build up a lot of charge, right? Why do you think you might want to do that? Well, you can kind of think of this almost like a temporary battery. It's sort of like a temporary storage device for electric charge. In between this plate, because you've got so much charge, you're going to have a very strong electric field in there. And that electric field is kind of like stored energy. So that stored energy is stored in the form of that electric field there. And when you decide to bleed this stored charge out, maybe at a later time, then you can kind of gain that energy back that you were storing in the first place. So the most common example that I can think of when you would want to use a capacitor, well, they're used in everything, okay, first of all. But the thing you probably have a lot of experience with is your camera. Your, not your digital cameras like your iPhones, but your actual point and shoot camera where you can hear it. When you hear it charge up, you hear that whiny sound like, it's getting really, really whiny. What's going on there is a lot of electric charge is coming in from the battery and filling up a whole bunch of capacitors. There's a lot of capacitors in there and they're wired up together. And they're charging those capacitors, getting them really, 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 really charged. And then notice on your camera, it takes a few seconds for that light to come on to tell you, all right, ready to go with the flash. That light takes time to charge up because these capacitors take time to actually accumulate this charge. The reason that you have to accumulate that much charge in a capacitor bank to fire a flash is because that flash bulb is actually a little bit of gas inside of a bulb, basically, and it takes a lot of electricity to jump in there and basically cause that gas to ionize, for the electrons to jump around and release all that white light. So if you hook your battery directly up to the flash bulb, nothing will happen because there's not enough. You need it to happen like it's instant. It's like shuffling your feet across the carpet. You build up that charge and you touch the doorknob, and at that moment it's like a little lightning bolt went off and jumped across to the doorknob. Same thing for the flash. You've got to accumulate a lot of charge there and then release it all at once into that gas that's in the flash bulb, and then whammo, the gas releases a lot of light, and you can do it over and over and over again. This is probably one of the most intuitive ways you could think of when you would want to use a capacitor. So it's a storage device. You put charge in, later on you can take charge out. That's the simplest thing. The energy that's stored in a capacitor is because of the charge on the plates here that are not touching, but also in the electric field that exists in between the plates when you charge it. Because when you put all those charges there, that electric field is going to be there anytime you put those charges there. So if we look at this picture of a capacitor that we have on the screen now, you can see what they sort of look like. A lot of times there's different shapes and sizes, but this one, you can see the shape there. And notice that the value of the capacitance is written right there on the side, so there's no fancy bands or color codings to decode. Usually for a capacitor, the value is written directly on the capacitor, so you can see that here. And they all come in different shapes and sizes. A physically large capacitor would be able to basically store more charge. A physically small capacitor, which might be inside of your computer, may be more delicate, may not be able to charge as much, but that's okay. You may not need to charge that much for your application there in the computer. There's a lot more uses for capacitor than flash bulbs, but that's the basic idea. Very, very common circuit component. All right, let's go on to the next most common thing that you'll see or you'll hear of, and that's called an inductor. Inductor is probably something you may not have heard of unless you're a circuit buff or something, you've been studying this before. Lots of people have heard of volts, lots of people have heard of resistors, lots of people have heard of capacitors, even if it's just from a movie you may have heard of. But not that many people have heard of inductors unless you really have kind of studied circuits a lot. So an inductor in its simplest form, let me go ahead and write this down. It's called an inductor. It's got really a cool name actually, inductor, like a conductor, but it's inducting something. It looks like this. It looks totally different than any of these things. You go here and you basically draw like a little spring. It looks like a spring, but really it's representing a coil of wire. And the units of an inductor is the Henry. And you'll see that as H, the Henry. Now, of course, you might have microhenries, you might have millihenries, you might have nanohenries, you might have kilohenries, you might have different modifications to the base unit for metric system. But the base unit is a Henry. Now, what do you think this coil of wire could possibly do? Well, I'll tell you. If you think about it, you have to think a little bit back to physics here, okay, a little bit with me. So I'll give you a little bit of a basic physics lesson. What you do when you coil a wire like this, let me back up from a coil. Forget about coil for a second. If you have a straight wire, just a straight wire, and you run an electric current through it, then nature is going to produce a magnetic field around that wire. You don't have to do anything. You don't have to design it specially. It's just fact. A magnetic field, just like your magnets that are stuck on the fridge, will pop up and exist as soon as you run an electric current through a wire. If you hook a 9-volt battery up to a wire and you get some current going, if you had a magnetic field detector, you would detect a magnetic field around that wire. Now, it turns out that energy, right, the potential to do some kind of work, is stored in that magnetic field, just like there was energy stored in this electric field. So it's something that's maybe not quite so intuitive, but if you think about two magnets and you're holding them apart like this, and you're physically holding them apart, right, because they're trying to attract one another, well, there's energy in that magnetic field. It's trying to pull those magnets together, and you are resisting that. So you know that there's energy, there's potential to do work in that magnetic field because you've played with them. You know that they push and pull and all kinds of things. So a magnetic field can do bona fide work, right? So what we try to do when we construct an inductor is we try to make a device, and this is important, that will concentrate that magnetic field and make it stronger so that we can store even more energy inside that magnetic field. And that is exactly what an inductor actually does. Because if you take that wire and you look at its magnetic field, it goes around the wire. But if you take a wire and you coil it up like this, then if you can think of a cylinder, like think of a cylinder coming from me to you, and I take a wire and I wrap it around the cylinder, like think of a paper towel tube or some kind of pencil maybe, and I wrap a tight wire around this cylinder. Like maybe I do 100 turns, maybe I do 500 turns, maybe I do 1,000 turns, maybe a really small wire, and I wrap it 1,000 times like this, all the way from me to you. Then it turns out that if you run an electric current through this very long coil of wire, that the magnetic field inside that coil, inside the coil, is going to be very, very strong. And the stronger the magnetic field, then the stronger and the more energy is stored in that magnetic field. So what you're doing is you're creating a situation where the magnetic field adds together inside and gets very strong. And so that's what an inductor does. It's a storage device to store energy, but not in the form of an electric field. It's storing it in terms of a magnetic field. Of course, electricity is what's generating the magnetic field, and that's why it's useful in an electric circuit. But ultimately, the energy that's stored in an inductor is because of the concentration of that magnetic field inside of the inductor. So that's a lot of theory. Now, if you were to look at a picture of an inductor, literally it's a coil of wire. So it's literally a coil of wire. That's all it is. You could build one in your house. Now, the more turns you have on that coil, the higher the inductance is what we call, so the more henries you have. And also, if you put different materials inside of this coil, you're going to affect the inductance. If you put metal, of course you have an insulated wire, you don't want it to touch the metal, but if you put a metal in there, it's going to concentrate the magnetic field a little bit more, you're going to change the inductance a little bit, and so on. So there's different ways to construct them, but ultimately you're just trying to make that inductance a specific value for your application. All right, so before I go on, I want to give you another little bit of philosophy here, kind of give you the big picture, because this stuff, this capacitance and inductance stuff, students don't usually learn about any of this stuff until weeks or months into their studies of electricity, right? Because it's usually just focused on resistors, 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 and we're going to do the same thing, but I really wanted to give you some motivation. Step back with me for a second and realize that a capacitor and an inductor are really nice mirror images of one another when you think about it, right? I told you a capacitor is constructed to basically concentrate the electric field inside the plates to store energy in the form of an electric field between the plates. The inductor is specifically constructed to store energy, but not in an electric field, as a magnetic field that's inside the coil. This guy stores energy as an electric field. This guy stores energy as a magnetic field. Electricity and magnetism kind of go hand in hand. Heck, I even already told you that an electric current generates a magnetic field, right? It turns out you can also generate electricity from magnetic fields. In fact, that's how our generators work at the power plants. You have steam that turns a generator. Well, inside the generator is a bunch of magnets and a bunch of wire. And when you turn them like that, out pops electricity. So electricity and magnetism are tied at the hip. You really can't have one without talking about the other. And it's a fascinating part of nature, you know, that they're invisible and we know they're there, but they're somehow tied at the hip. What we do with these two guys is a lot of times we put them in circuits together to perform a function. And the best example I can tell you of when you would really use an inductor is when you would put it in a circuit with a capacitor to build a radio. Now, I'm not talking about the digital radio, it's a fancy stereo system. I'm talking about, think about to older radios when you can open it up and see a bunch of wires running around everywhere. There was no computer chips in the early radios. I'm talking about your basic radio. You're basically going to have a circuit in there that's going to try to receive signals over the air and play them through a speaker. Well, inside of that radio, you've got capacitors and you've got inductances. And you have chosen those values such that when you turn the knob, by the way, when you turn the knob, usually you're changing the value of the capacitor in the circuit. When you turn the knob on the radio, you're changing the value of this capacitance. When you do that, these two guys are in the circuit together, and it's kind of hard to explain without showing a real circuit, but basically, since this guy stores energy in an electric field, and this guy stores energy as a magnetic field, when the wave comes in, you get this situation where they start sending energy back and forth to one another. The capacitor sends energy into the inductor, and the inductor kind of collects that energy. And then on the next cycle, it sends the energy back to the capacitor. And it goes back and forth in this perfect harmony. It's called resonance. It's very perfect harmony when they kind of send this energy back and forth. And at that moment of resonance, when they are both doing that perfect dance of sending energy back and forth, that is the frequency of the wave that you're receiving, and that's what gets sent to the speaker. So it's kind of like you can think about the wave comes in, hits the antenna, and goes to these capacitors and inductances. Of course, you can tune the knob and change the value of this capacitance, and when you do that, you're changing the way the circuit behaves so that that frequency that you want to, the radio station you want to listen to, is the one that gets sent to the speaker because of this perfect dance of energy between the capacitor and inductor. All right, that's about as much as I want to say about it, because honestly you can't truly understand it until we do a lot of math and a lot of equations. But big picture, that is what's happening when you tune a radio. You're changing this value of capacitance to perfectly resonate or tune with the inductor that's also there, thereby letting that particular radio station get sent onto your speaker. And that's really what it's mostly used for, at least in terms of, you know, radio technology. But inductances, of course, have lots of other uses as well. All right, so the next circuit component, certainly these are the most common circuit components. You could spend a year studying circuit theory just with these four components, and I could stop here. In fact, I thought hard about stopping here because we're not going to talk about the other circuit components that I'm about to draw for you for quite a long time. But I did want to give you an overview, give you a little motivation. The next circuit component that's very, very common is called the diode. And a lot of you may have even heard of what a diode is. Basically, a diode only allows the electric current to flow in one direction. It's like a one-way switch, right? It will not let electricity go this way, but it will let it go that way, right? So let me show you what that looks like. Number 5, we call it a diode. Diode, just like that. All right, now a diode, the symbol for it looks like this. You've got a triangle with a line on the end of the triangle like this. It would look just like this in an electric circuit. Now, when you see it drawn like this, what this means is current can only flow, only flow this way. In other words, if I hook a battery up to the circuit and try to let current go this way, it will be able to go this way. It will go this way all day long, no problem. It's like a wire. It doesn't present much resistance. It doesn't get in the way. It just lets it go that way. But if I take that battery and turn it around and try to force electricity to go this way, it will not flow. It will not flow that direction, all right? Now, if I hook a big enough battery to it or a big enough generator to it to kind of like overpower this thing, sure, I can do that. I'm gonna burn it up. Literally, smoke will come out of it. It'll burn up, and then, of course, lots of things can happen then. But in normal operation, it's only going to let electricity go one direction. There's tons of applications for that. I can't really get into them now because you have to draw a big circuit to show you, but I think that even though you may not know the specific applications, I think you could see the utility of something like this. Think of the hardware store where you might find a valve that only lets your water go one direction. There's lots of reasons you might use that if you're building a sprinkler system, right? Same thing in a circuit. There's lots of reasons when you would not want current to go a certain direction because maybe it'll damage a component, or maybe that part of the circuit that you're designing, you only want current to go one way. So you just stick a diode in there. It's not going to affect anything this direction. It's going to let everything work normal, but if any kind of current tried to go the other way, it's going to block it. And that's a very useful thing. So that's what diodes are used for. The next guy after a diode that I know all of you have heard is called an LED. Lots of people have heard of LEDs, but not as many people know that LED stands for light emitting diode. So if you know that already, congratulations, it's light emitting diode. But a lot of people do not know that LED stands for light emitting diode. So it's a diode, just like this one, that also happens to emit light. That's all it is. So if you were to draw it, it would look just like a diode with one small change. You have a triangle like this, but you have, on a circuit diagram, you would see two little squiggly lines, maybe one, maybe two, depending on who's drawing it. This represents the light that's coming out of this diode. So this basically means that if I hook a battery up this way and let the current go this way, because this is the direction I can allow current to flow through this guy, then the current will flow and light will come out as a byproduct. That's just constructed that way. They're built in the lab that way so that when current goes through, light is generated inside and comes out. The details of how that works is totally for another course. That's very, very amazing discovery in the 20th century, actually, to build these things, but that's how they work. There's no light bulb filament inside there. It's just the way the thing is designed with the silicon that's inside of there. All right, but if I turn my battery around and go the other way, then nothing happens. No current can flow, no light comes out. So it serves a double function. It serves the electricity blocking feature, and it also happens to emit light. Now, it's useful for lots of different reasons, but of course you see these things all the time. Almost every electric device out there has a little red indicator light or green indicator light or a blue indicator light. Those are just different kinds of LEDs that are built slightly differently to emit light with a different color. All right? Okay, so here's a picture of a regular old diode. It's just a discrete component. It's about the size of a resistor, and notice that there's a band on one end. That band is telling you where that flat piece comes from that's on the front of that triangle. That tells you that the electric current flow can go this direction, from this direction to the direction that has that band on there. That's telling you the orientation of the diode. All right. Now, here's a picture of a light emitting diode. You can get them in all shapes and sizes and also in many colors. And you can see from the color of it that if you send electricity through it, the thing will light up. If you hook your battery up the other way, no light's going to come out, and obviously no electricity is going to flow through it either. Okay, the next electric circuit component that's got so many uses is one that I know that every one of you that is watching this has heard of, and it's called the transistor, right? So transistor, lots of people have heard of transistors, but not many people, unless you study this stuff, really know what they do. I mean, you know transistors are in radios, you know transistors are in cameras, you know transistors are definitely in computers and on computer chips, right? You've heard of those transistors, millions of transistors on a computer chip. You know that they're in memory sticks, you know they're everywhere. And truthfully, most of the technology of the last 50 years is a direct result of having learned how to build these things we call transistors. So they're so incredibly important, it's hard to overstate their importance, to be honest with you. What does a transistor do? Big picture. It can do two main things. The first thing it can do is it can act as sort of like an electronic switch. Normally a switch in a wall socket or something can be open, and I can open the circuit, and you can close the switch and that will let the circuit function. A transistor can also function as a switch, but there's nothing physically moving inside. It's just how it's built, and I'll show you in a second sort of how it works. But it can act as a switch. That's the #1 use for it, and that's mostly how it's used inside of a computer, and all of the things that a computer can do arise because of the behavior of transistors. A transistor's second function, right, is that it can act as an amplifier. So literally that is when you turn the volume knob on your stereo system, you're basically manipulating those transistors in there to push out more current. So a transistor can take a teeny tiny input signal, like your voice, right, maybe coming in on a wire, and it can make a direct replica of it on the output, but much bigger, much higher volume level, for lack of a better word. And that goes into your speakers, so when you adjust your volume, you get a nice, rich, beautiful, loud sound. That's a direct result of a transistor, right? So two functions of a transistor, switch and amplifier. Now, how do you spell this thing? It's called a transistor. All right, now there's actually lots of different ways to draw transistors. Actually, there's lots of different types of transistors, and we're not going to get into the types right now. But the basic way you draw a transistor is like this. It has 3 terminals. So here's the first wire. Here's sort of like the second wire that kind of comes in at an angle. It's just the way it's drawn. And the third one goes out at an angle, and you have a little arrow here. Now, depending on the exact type of transistor you have, the arrow might be in a different orientation, and actually this little symbol here with the angle coming in and coming out may look slightly different. But by and large, this is the basic symbol for a transistor. It has 3 terminals. You have this terminal here, a terminal coming out here, and you have a terminal going out. So if you look at a real transistor, you know, that we'll show you here in just a second, you'll have 3 wires basically going into the thing. All right. Now, I'm not going to get into transistor theory here, but basically what I was saying a minute ago, if you're sending your voice in over a wire, let's say, you may have a very small voltage signal coming in on that wire, right? And the way you send the input comes into this leg right here. The output has current flowing down through the thing like this. This is sort of the output like this. If you stick a voltmeter here, you might see something that looks like this, much larger. But it's a direct replica of the input, and that's how it behaves as an amplifier. So I might send a small signal in, a voice signal or any other signal over this guy, and you have to obviously design the circuit around the transistors. There's many ways to do it. But basically the input gets replicated at the output, but just much bigger. So you're sending more current, more power to that, whatever you're doing. I'm thinking in terms of voice amplifiers, but there's amplifiers in all sorts of electronics that don't have anything to do with voice. You may need to make some signal larger or even make it smaller. And transistors can do that. And that's the main function of it in terms of an amplifier. Now, if you think about it, in a digital system, right? In a digital system, you have an on or an off, a 1 or a 0, right? So you won't have this nice wave, but you might have a on going straight up and an off going back to 0. And when you push this through, the output is going to be on or off. So when I send an on signal here, I'm going to get an on signal coming out. When I send an off signal, like a 0-volt signal here, I might get an off signal coming out. So this part of the circuit here does not function. Nothing happens here unless I actually turn the on signal on coming in here. If I take this away, no current flows here. if I send a voltage in here, then this part of the circuit turns on. So that's how it behaves as a switch. It's directly a result of how the thing works. It's like if you send a signal in here, then a signal comes out the other end. So I can isolate parts of the circuit. Like maybe I have an entire thing going on over here, a fan, a motor, maybe I have 50 more transistors here, maybe I've got something crazy over here, but I've isolated it through this transistor. This guy's not even functioning unless I turn it on by sending a signal in here, right? So that's how it behaves as a switch. Now if you take 4 or 5 million transistors and build a computer chip that are basically arranged to allow these transistors to be interconnected in ways that are beyond the scope of this discussion, but basically they're interconnected like that, then you can do lots of great things with transistors. You can create machines that add numbers together, which is basically what a computer does. And if you create millions and millions of transistors in there, then you can do lots of calculations very, very, very quickly. Because these transistors, and this is really the important part, they turn on and off extremely fast, much faster than a mechanical switch could ever do. So transistors can amplify a signal, and they can also act as a sort of a discrete switch, switching things on and off at extremely fast speeds. And that's really why they're so useful in computers, because they can operate really fast. So these computer speeds that are going higher and higher every year is a direct result of pushing these things faster and faster and putting more of them on the chips. And as you study electronics more and more and more, you'll learn how to connect these transistors together to do things like build memory chips, build computer chips, and so on. All right, one final guy I want to talk about is something that everybody's heard of. It's called a transformer. Now, I'm not talking about the giant robots that you see in the movies. I'm talking about the transformers that you might see up on the poles, right, on the side of the road, those big cans, right? Those are usually transformers. Basically, a transformer allows a voltage to be increased or decreased to another voltage inside of a circuit. Specifically, they work with those AC signals, the ones that go up and down. We talked about AC in the last section. So the symbol for a transistor might look like this. Maybe you've got a coil of wire here. You've usually got something in the middle. You can usually denote it by some lines. This is like an iron core. And then over here you might have maybe less coils. That's why I haven't drawn it this way. Maybe fewer coils, or maybe you have more coils. Depends on what you're trying to do. But if you send an AC signal in here, which is a signal that goes up and down, right? Then what's going to happen is, and these things are wound, I should say. There's a core here, usually it's an iron core or something, and this coil of wire is coiled around it, and the other coil is also coiled around it. Of course, the wires are not touching. They're all insulated, so they're not touching, but they're wound around a common core. So what happens basically is when you send the AC signal through here, you get a magnetic field that is flip-flopping back and forth because it's oscillating back and forth. And this magnetic field interacts with the second coil and generates a voltage in the second coil. And you can increase or decrease that voltage depending on how many turns you have on this coil. So basically, if I have a wall socket that's 120 volts, let's say, and I'm building something, but my circuit that I'm building only needs maybe 10 volts, AC 10 volts, let's say, then I'm going to need to change that voltage from 120 volts down to 10 volts or whatever I'm trying to use. I'm going to have to, I can't hook it up directly, I'll blow my circuit up. I need to step it down. So I might create a situation with a transformer where I will go in and basically have the current go into one side of this coil, and an output on the other side. The output would be over here, might be a different voltage than what I'm putting in. So that's its main focus and its main use, is to step up or step down the voltages. And that's why you see them on the side of the road, on the telephone poles, on the poles on the side of the road, because they're taking that high voltage coming in from the power plant and they're changing it to a lower voltage to come into your house. So that's what that guy's used for. So if you wanted to see a picture of that, here's a picture of a transformer. And basically you can't see that much, but inside of there is some kind of a metal core. And coming in one side, you've got a winding, and coming in the other side, you get a winding, and you hook it up in your circuit, and there you go. So you have to design your transformer. There's a lot of design that goes into it to get the exact function that you're basically seeking. Now here is a picture of a transistor. They're really not much to look at. They certainly don't look like what the picture I've drawn on the board is. But you can see that it's a device that has sort of like a black component at the top, and there's 3 legs to it. And the details of how you identify these legs will come as you study these things later. But basically one of the legs is the input, so to speak, and then the other 2 are the ones that are on the other side of the device that basically are in the output. So depending on what you're trying to do, you'll hook it up different ways to be able to turn on the transistor and to send the output to wherever it is you need it to go in the circuit. So I hope you've enjoyed this overview of basic circuit components. This is not an exhaustive list of circuit components. There are actually more of them, but they're not used as much, and they're used in situations that you'll need them when you need them, but they're not something that's in your back pocket every day for everyday uses. So this is not an exhaustive list, but it's a very good start. If you understand the basics of these things, then I hope you can see how amazing circuits can be created to do various uses. So basically you have the sources, which are the voltages. You always have a plus minus either printed on there or implied in the diagram. You have a unit of volts. You have resistors, which resist all current flow to various levels depending on the value in ohms. And it has the kind of a jagged line like this. Capacitor is the unit of the farad. You commonly see microfarads or even nanofarads. And they're not physically connected here because the charge is allowed to pile up in there and store energy in the form of an electric field. The inductor is simply a coil of wire, in many cases with some piece of metal inserted inside of the coil. The purpose of this guy is to store energy in a magnetic field. It's sort of the exact dual of the capacitor above it. We talked about when you might use that. The unit is the Henry, but of course you might see microhenries or millihenries or whatever it is you have depending on what you've designed. We have a diode. It allows current to flow only one direction. If you flip the current direction around, try to hook it up backwards, nothing's going to happen. No current's going to flow. Then we have the light emitting diode, which is exactly the same thing, but also emits light of whatever color you've designed whenever electric current flows through there. Then we have a transistor, which is basically something that functions as either a switch, which can be on-off, or as an amplifier, taking an input signal and making it large. So you can think of all kinds of situations when you might have a transistor. Of course, you put them together in banks and create computers and memory and all kinds of things. And we also have a transformer, which is literally taking an input voltage and changing it to an output voltage depending on what you need inside of your circuit that has an AC signal like that. So these are the most important ones, folks. I mean, honestly, I didn't really have to do this section because what we're going to do from here on out is really study resistors and sources and really understand how these circuits are constructed. So I could have skipped this, but I really wanted to give you some motivation. I really wanted to show you that it's not hard to understand what an inductor does. It's not hard to understand basically what a transistor does. And if you stick with me and if you learn these things, you'll get very good at this stuff. And when you get onto the more advanced courses and you'll be designing amplifiers, you could literally go to the store and buy some transistors and buy some resistors and capacitors and hook them up and make your own amplifier. You could literally do that once you understand how circuits work. So that's why I find them fascinating. So watch this a few times, make sure you understand it, and then follow me on to the subsequent sections where we'll start to really roll up our sleeves with the basic laws of electric circuits and how to analyze them. Learn anything at mathandscience.com.